Good afternoon, everybody, and welcome to the Bureau of Economic Geology Summer Seminar Series. I'm Evan Civil, and I'll be your host today. Today, our speaker is Dr. Mark Shuster, the Associate Director of the Energy Division. Mark is responsible for managing the Bureau's energy-related research. He's been actively involved for the last 1.5 years in initiating and coordinating the Bureau's research efforts in hydrogen, geological storage, and related topics. He joined the Bureau in September 2016, and prior to joining the Bureau, Mark worked for Shell and affiliates for 30 years in upstream E&P roles from around the world. Mark began his professional career as a research geologist working on projects in the Permian Basin, Atlantic Margin Basins, and Southeast Asia. Subsequently, Mark worked on exploration and appraisal projects in Australia, the Middle East, Gulf of Mexico, Latin America, and Alaska. Mark received his Bachelor's of Science degree in geology from the University of the Pacific and his PhD in geology from the University of Wyoming. He and his wife, Cheryl, are blessed with 2 kids, their significant others, and as August 7th, a granddaughter. Mark is still trying to cope with the implications of bearing the label granddad. So without further ado, I'll turn it over to Mark.
That's really odd. The nature of the summer seminars where people are talking about vacations or their hobbies. I would have something perhaps more interesting to talk about, but listen, I actually find hydrogen very interesting, and these days it's as much as a hobby as it is part of what I'm doing here at work. So with that, let me just go to the next slide. And for those of us, and there are a few of us here that are close to what's going on in hydrogen, we stay aware of what's in the news and what's coming out in terms of potential funding opportunities. But for many of you who may not be close to it, I just want to let you know that this is very active, both in the media space, as well as in future funding space, as well as in the industry. Lots of activity on hydrogen in many different fronts, supply, storage, looking at economics, covering the whole spectrum of activities. And, it's also an important part of what we're seeing is future funding opportunities for the Bureau and broadly. The news that we saw a few weeks ago with the bipartisan infrastructure bill from the Senate indicated that there would be $1 billion of appropriations for hydrogen R&D. In June, Secretary Granholm announced the Hydrogen Energy Earthshot program. I'll talk a little bit more about that later, but this is a very active topic of interest. So today, what I really want to focus on is the spectrum of supply. And we at the Bureau in our working group, not really doing a lot of work on supply. We're doing some, and I'll talk about that. But it is important to understand, what that spectrum comprises, understand a little bit of what the existing production sources are, and also some of the anticipated ones, the ones that are on the favored list of winners going forward. And importantly, though, I think it's worth us having at least some awareness of alternative sources. And that includes native hydrogen or naturally occurring hydrogen. Also includes some topics that haven't gotten a lot of airplay lately: underground coal gasification, in part because it has coal as part of it. It has not received much attention recently, although it received a huge amount of research dollars over the last several decades. And in situ combustion, which is one topic that we are working on here at the Bureau, specifically by Ian Duncan and Bo Wren and others. And so this is what I want to discuss, because I think it's important to get an overview of what's out there in terms of supply, and also have a better appreciation of what the opportunities are. So this is one of my favorite slides. It comes from the Department of Energy. maybe I like it because it's complex, but it's really meant to illustrate the flexibility of the hydrogen systems. And the reason that we're focused on hydrogen is that we see this as an energy carrier for the development of a low carbon economy in the United States and broadly. And it has hydrogen has many really positive attributes. It's transportable. It is storable, and this is one of the more important aspects, particularly given that it provides for indefinite storage duration, which means seasonality. You can store it effectively forever. It's a molecule and then burn it when you need it. There are multiple sources, and that's what we'll talk about today. And it offers low carbon emissions. Now, as I'll mention, most of the hydrogen that's currently being generated is coming from fossil fuels. With the integration of carbon capture and storage, the hydrogen that's produced can be viewed as low carbon. So that's kind of still to come, but it's definitely doable. And then probably what has got most attention globally as well as in the US is the potential to generate hydrogen from renewable sources, including solar, wind, hydro, and anything that where you can generate electricity, and nuclear as well as geothermal. And that comes with, I wouldn't say completely no carbon, but low carbon as well. A lot of our work at the Bureau is really focused on the geological storage aspects because of the volume capacity that the subsurface allows. That's been touched on in previous talks. I'm not going to go into that into any detail, but that's a large part of why we are interested in hydrogen here. So let's just take a second to go through, what the current state of hydrogen production is. And before I do that, just to give you a go by, because we'll be talking about metric tons and kilograms of hydrogen. And for those that haven't been working in hydrogen, these units and terms may not mean a lot. I certainly had that when I first got into this work. So a kilo hydrogen has an energy equivalence about a gallon of gasoline. So that's a good go by. So when we talk about kilogram, think a gallon of gasoline. When we talk about a metric ton, think 1,000 gallons of gasoline. And for those that are in the gas business or gas research, there's about 2.3 metric tons of hydrogen in a million standard cubic foot of hydrogen at standard conditions. So that's important because as we talk about the production, like how much is being produced, both in the US as well as globally, I think you need to try to get to grips on what that actually means. So right now, currently, there's about 10 million metric tons of hydrogen produced in the US and 70 million metric tons globally. Almost all of the hydrogen, as I mentioned previously, is being produced from fossil fuel. Most of it is coming from natural gas. Some, and the large part of that is coming from coal gasification in China in particular. So some of you may have come across talking about the color spectrum of hydrogen supply. And in talks that I've given on this, I disclose in full transparency that I'm colorblind. I am. But I'm also colorblind to some of the subjectivity that goes into designating these sources of hydrogen supply with various colors. So, but it's out there in the public domain, it's in the literature, so it's good to know. The ones that you'll come across most are green, which are the hydrogen that's produced via electrolysis from renewable energy sources. Blue, which is hydrogen coming from predominantly natural gas with carbon capture and storage. And then also referring to gray, where basically this is where most of the hydrogen is being generated right now, which is from natural gas, but without CCS. The costs range basically from a little more than $1 to more than $13. The next slide, I'll show you what that looks like for each of these sources of hydrogen. And then below, you can also get a sense of the emissions content in a relative sense. So, well, what, of course, we're focused on for future low carbon economy is to look at the sources that provide no or low CO2 or greenhouse gas in general. So here are the cost data that the DOE is compiled or estimated, and it basically ranges from the lowest cost, which is coal gasification without carbon capture and storage, coming up to solar electrolysis. And the focus right now from the Department of Energy in the US and elsewhere around the globe is trying to reduce the cost, particularly of these electrolysis sources, down. And the DOE announced what it's called an Earthshot, a hydrogen shot, where it wants to lower the cost, production cost of hydrogen from electrolysis down to $1 per kilo within the next decade. So let's just briefly touch on some of this. And this is, for those that saw JP Nicole and Peter Eichel's talk earlier in the year, there's a little bit of a follow-up presentation from that presentation that was given. But it's worthwhile just refreshing your memories of what we're talking about. So the predominant form of hydrogen generation in the globe is steam methane reforming. And this chart taken from Lindy just basically shows a simple schematic of how that works. You've got water that you need for steam. You've got the feedstock, which is predominantly natural gas. You need that also the fuel to create the energy to produce the steam, as well as to allow the reactions to occur. And that can be done within a steam methane reforming plant, which is shown on the right. For those that are interested, these are the two important reactions. There are many, many others involved in this process, but you have the steam methane reforming reaction, and then you also have the water gas shift. And effectively, this drives generation of hydrogen from the natural gas. Coal gasification is the next big source of hydrogen in the globe. As I mentioned, China is the biggest user of coal gasification for hydrogen generation purposes. So it has about 85% of global hydrogen that's generated from coal gasification. This is a fairly complex schematic, but the points to focus on are that you're essentially gasifying the coal. You are going through creation of syngas. From that, you're separating out the hydrogen from the other synthetic gases that are created. And then that hydrogen can be utilized for fuel cells, electric power generation, whatever. And the guiding critical reactions are shown below. Basically, you have coal and oxygen with some heat. You generate carbon monoxide and hydrogen, and then you go through an additional reaction where you're taking carbon monoxide and water and generating CO2 and hydrogen. So those are the two biggies. Now, electrolysis is the one that, as I mentioned, is probably getting the most interest. And just to refresh maybe some of your high school or junior high school chemistry, this is electrolysis at work. And I would encourage all of you to go home tonight and run a little experiment, grab a AA battery that I've showing there and put it in a glass of salt water, and voila, you are conducting an electrolysis experiment. Because what you're seeing here is that on the cathode, the negative terminal of the battery, you're actually generating bubbles of hydrogen like that. And you can prove to yourself that it's hydrogen by igniting it. Proof. And basically, this is the basic process that's driving all of the renewable electrolysis. Now, of course, you're using direct current from a wind turbine or from another source of electricity to do that, but the same principle. So here is an example of anticipated and developing, and probably one of the ones that's getting the most attention right now, which is using wind, including offshore, to effectively generate electricity, and from that electricity generated through electrolysis, generate hydrogen. And there are a couple of schemes as shown here. One is you can have the offshore wind farm and electrolyze offshore and then pipe in the hydrogen for whatever usage you're envisioning. The other is that you basically use electrical cable to allow the current to flow to the onshore and then have your electrolyzer located onshore. So there are pluses and minuses depending on costs, and but this is a scheme that is getting a lot of traction currently. What I find really exciting is the potential use of dedicated small modular nuclear reactors to generate hydrogen. And we have here at the Bureau have been in discussions with a company called NuScale Power. We've actually co-submitted a request for information to Department of Energy with some thoughts about combining their scheme with generation with some of our ideas of geological storage. But they have a really nifty model. There are other companies out there that are developing small modular reactors, but what they're developing and testing are these modules, which are effectively self-contained reactors, which then can be put into a complex with multiple modules where you can effectively generate from that power, both thermal and of course electric with turbine. And the scheme that they have published on, and we've discussed with them, is using their power module to generate steam, to run a turbine and a generator. So they can create a steam from that, run that into what's called a high temperature steam electrolyzer, and also with electricity to power that electrolyzer, add water, a lot of water. You need about 9 units of water for every unit of hydrogen you're going to generate. And then you're creating oxygen and hydrogen from that. And with a dedicated system, so in this case, a 250 megawatt thermal module, you can generate on the order of about 50 metric tons per day of hydrogen. So, this allows for a dedicated hydrogen production as an energy carrier that could, if the cost is reduced, could allow for development, of hundreds of these and generate a lot of hydrogen for other uses. So now I want to transition and talk about other sources. And again, for those who saw JP's talk, he actually showed a version, something similar to this slide. And hydrogen is abundant on Earth. And, you know, it's the most abundant element in the universe. There are seeps and occurrences of hydrogen globally. So there's a lot of it. The real question, and I've been asked this many times, you know, are there economically viable accumulations of hydrogen? So in other words, could we explore and produce hydrogen that's accumulated naturally? Well, we need to step back and just think about the proposed origins and processes here. And I'd say propose, a lot of these haven't been proven yet. Some clearly are, like the serpentization, clearly a source for hydrogen. We know hydrogen is expelled in volcanoes and vents globally, and then other ways that, including potential mantle sources where we can generate hydrogen. The specific questions that we need to ask, you know, with these processes in mind, you know, can we concentrate high percentages of hydrogen through these processes? Can we trap this hydrogen in a reservoir? In other words, a reservoir with some sort of seal on top of it. Can we preserve the hydrogen through geologic time? And as I mentioned previously, can we economically explore, find, and develop hydrogen accumulations? So there have been many occurrences of hydrogen being tested or discovered in wells. One example is from a number of wells, touch on this specific well, Wilson well, but along the Nemaha Uplift in Kansas. Here's a cross section. Essentially, you have this basement high, which is driven by a deep-rooted fault that's running north-northeast. And you've got both Paleozoic reservoirs as well as basement reservoirs here. Now in Kansas, you also have oil and gas that's actually trapped in basement. So it's, you do have economic traps within the basement. And this one well, Wilson, actually sampled some hydrogen, only were about 10% of hydrogen. And what's significant about this one, and there are other water wells in the area that have encountered very low pressure hydrogen, but this seemed to be at pressure. So yes, you know, it can be trapped. You can find it. There's just, from a percentage perspective, not a lot of it in these cases. The one accumulation that's probably piqued geologists' interests the most is one from Mali. It's a Bourakebogou field that's lying in the Tambura Basin in Mali, which is situated here in inland Western Africa. This was an accumulation that was accidentally discovered by a water well. It's kind of a fairly common practice, I guess. But when they're drilling a water well, they had an explosion, and then they eventually realized that the gas that they ran into was actually hydrogen. It's an interesting configuration because you have interbedded Proterozoic sedimentary rocks with doleritic sills. So these are igneous rocks, for those who might not know. And it's basically this intercalation that provides both for reservoir and also some intra-reservoir seals. The other interesting piece of this one, and maybe the real controlling factor of why it's hydrogen, well, first off, it's a shallow accumulation, and we'll touch on what the implications of that are in a second. But you have these deeply rooted flower structures or fault systems that are going into Precambrian basement, and they effectively set up the structures for this accumulation and potentially some other accumulations in the area. The challenge here is, well, we know it's hydrogen. It's been tested, 98% hydrogen. But if you look at the test results, you know, you've got a shut-in pressure of 58 psi, flowing pressure of 36 psi, and a production rate of 50 standard cubic feet of hydrogen per day. So for any of those that have worked in oil and gas sector, you kind of go, well, that's awfully low. You know, and for those that might not be familiar, just think that your tire on your car has a pressure of about 32 or 35 psi. So it's about the same pressure as the tire that you're driving around on. So it's low. Anyway, so just a point to note, that's what's been discovered, and it's a low pressure accumulation, but there is a discovery of hydrogen. Chris Boreham, who's at CSIRO in Australia, has put out a really nice paper talking about kind of the potential for exploration and production of hydrogen, mainly focused on Australia, but they've done some very good work to assess, you know, what some of the controlling factors could be. And this diagram shows what they envision as potential abiogenic gas traps here and a system. It also includes oil and gas. And some of the key factors they see as being important for this are you've got access to the Precambrian basement, probably through deep-rooted basement faults, and you have seals and reservoirs directly above basement. So with that, let me just make a few comments. So we've got a lot of hydrogen. There's a huge amount of hydrogen flux in the earth, but you know, we only have a few examples of trapped hydrogen accumulations. Most all, with maybe one or two exceptions, are low pressure. And we also have to remember that you know, basement seems to be critical here, but we've also collectively drilled thousands of wells in the basement and just haven't come across a lot of hydrogen. So, you know, it's definitely a scientific interest. Yeah, at least for local use, and this hydrogen is being used for the village there in Mali. You know, might have some limited economic viability, but so far it doesn't look like it's going to be a resource that is going to have much dent on the world's future need for hydrogen. So far. So now let's switch gears and talk about another topic that's kind of fallen out of favor, probably because of this word, coal. You know, in some people's vernaculars, coal is like talking about cigarettes or you know, some bad drug. But over many, many decades, there has been work on underground coal gasification. And here's a schematic. It shows you how that works. Right now, as far as I'm aware, I don't think there are any schemes that have working CO2 separation and carbon storage, but it's possible to do that. And basically within underground coal gasification schemes, excuse me, you're effectively doing like what you're doing in a surface coal gasification scheme, and that you're generating a synthetic gas. And here from all the tests, and I'll talk a little bit more about the tests that have been done, at least in the US for underground coal gasification, you can see the gases that have actually been generated. So hydrogen, depending if it's air or oxygen that's being injected, can range from roughly 13% to 33%, and then CO2 from 16 to 42% or so. So, but there are many other species of gas here. So that's the synthetic gas that's actually being generated underground. Well, the attraction was early on, particularly going back to the 70s and 80s when DOE was funding a lot of work here, was that there were benefits here, that potentially you could tap into a very large coal resource that we have in the US, and without mining, be able to generate energy or harvest energy, and then use that for other purposes like electricity generation. And then eventually the thinking was, well, you could also separate out the other gas species and just hold on to the hydrogen to use for low carbon purposes. There have been tests and plants developed around the world. I'm not showing all of them, just the countries with major plants or tests. There's actually only a couple of plants that are currently active, one in Uzbekistan, which I'll talk about, and one in South Africa. The other circles here would indicate tests that have been conducted on UCG. In the US, there were over 30 pilot projects. Some were repeat tests in different locations. So you're only seeing, I think, a listing of 15 here. And the major players for that were Lawrence Livermore, the University of Wyoming, University of Colorado, other institutes, including some work that was done way back when here at UT and also at Texas A&M. Now, a little bit of a personal note, and perhaps part of the reason I'm interested in hydrogen, I actually ended up at graduate school at the University of Wyoming because the deal that I was offered included working on a UCG project with Arco Coal in Wyoming in the Powder River Basin as part of the acceptance to their graduate program. So it was a great deal. It came with a job and some other things, and I took it. So that's how I ended up at University of Wyoming, and started off in effectively coal geology or classic sedimentology, kind of based on that experience. Things changed, but that's where I started, and it was a life branch experience for me. So one of the plants that I mentioned is one in Uzbekistan, and this has actually been generating syngas since 1961. So it's been around for a long time. And they use that synthetic gas to run a 100 megawatt steam turbine, producing about 35 million standard cubic feet per day from this UCG process that they have. However, it doesn't have any CCS, and that's one of the issues with it. But one of the points this company, Link Energy, which is Australia-based, has purchased this plant, is that they say, well, look, there are some environmental benefits on the basis is that here's old mine scar. Here is where the UCG plant is. You're not disrupting the surface. Now, there are some other issues that go along with UCG, and I'm going to touch on those. So here's concerns, and actually there's a really great diagram that I found in a brochure from Friends of the Earth, did a study on UCG. I'll talk about that a little bit more, but it kind of highlights some of the issues that are associated with it. First, and we've already mentioned it, is CO2 or greenhouse gas generation. The other big one, and certainly in my experience with Arco Coal and Powder River Basin, was one that kind of shut down that test, was groundwater contamination. In that you're creating a lot of toxic or carcinogenic organic chemicals as you burn this coal. And if there is communication with aquifers, freshwater aquifers, then you have an issue. And it turns out in the case of the Powder River Basin, the coal seam itself, the Wyandotte seam, was actually an aquifer that was used for agricultural purposes. If you have the burn too shallow, then you also run into issues with subsidence. And a few of the tests have actually collapsed as a consequence of the burn because you're creating a cavity when the coal is burned. And then you also run into issues with just fugitive emissions from faults, fractures that you may not even know about that could allow for some of the syngas to escape. Now, Friends of the Earth's perspective is, look, okay, this all might be great, but they don't even buy into the fact that CCS is a solution. So that when you start the discussion with the statement that CCS is a false solution, then you're from their perspective, you're not talking about any fossil fuel sourced hydrogen that is being viable. So I don't buy into that perspective, but I wanted to share that with you. So now let's move on to in situ generation from oil fields. And this is an area of research that we're active in here at the Bureau, particularly driven by Ian Duncan and Bo Wren and others. And this kind of hinges on a discussion that Ian and I had, over a year ago, and we're talking about UCG, we're talking about in situ combustion, and he had been doing some work on in situ combustion for EOR purposes, so for enhanced oil recovery. And we came across a paper from some workers from BP back in the 80s, where they had conducted essentially an experiment at heavy oil accumulation, where they were injecting air and wet oxygen and steam, and ended up producing hydrogen. And so there's a little bit of serendipity here, but they did quite a bit of work to try to understand why they were seeing the hydrogen that was being generated. And based on the analysis that they did, interpreted the hydrogen as being produced by the methane shift reaction. So in other words, the steam and the reactions that I was showing with the SMR process previously. So the work that Ian and Bo were doing is really looking at, okay, is there a way now with some of this information that we can actually model and design and test ISC systems that are optimized for hydrogen production, and couple that with CCS, and in particular with some technologies that like membrane filtration that could allow for hydrogen stream to be produced, but keep the other greenhouse gases, in particular the other gas species, downhole, or at least let you remove them so you could re-inject them in another repository. And Ian, I just want to give a shout out to Ian. He was invited based on a presentation that we gave back in July by the DOE to speak as a panelist on the Earthshot Summit, which is coming up on the 31st of August and the 1st of September. So, and here's the link, and happy to share that with you. But I think it's great that this work is, and Ian is getting some notice. So just a little bit more on this BP experiment, just to get you oriented. Here's Alberta, and the tar sands are basically located on the eastern part of Alberta. And you've got these, basically it's a bitumen, so very high viscosity oil that's accumulated in relatively shallow depths, in this case about 450 meters. And this oil has been developed through various processes, including mining, surface mining, but in subsurface, gravity-assisted drainage processes with the steam heating to make it mobile, all sorts of different things. And that's the reason that the BP kind of came across this hydrogen production was on the basis that as they were doing the steam and air injection, they noticed, and I'm just showing the hydrogen gas species here, that at times, it was episodic, that they would see these pulses up and above 20% hydrogen concentration in the produced gases. And that's what has intrigued them and has intrigued us. We're not the only ones that are interested in this process. As a matter of fact, there's a group that I believe has their origins from the University of Calgary. It's a group called Proton Technologies Canada, and they have developed a process. They haven't published much on it, so we're not exactly sure of the details, and are going forward with a pilot ISC project for hydrogen generation in Saskatchewan. They have mentioned that they use a palladium membrane to separate the hydrogen from the produced syngas, and they're targeting, I don't know if this is credible or not, production costs of 30 cents per kilo of hydrogen, which would be really, really cheap. So we've gone through some of these alternative sources and favorite sources, like I like the small modular reactors for hydrogen generation. My sense is that we're going to need all of the above because when we look at the scale, if we want to have impact on reducing carbon production, greenhouse gas production in the atmosphere and through utilization of hydrogen, it's going to be a massive undertaking, really massive. And what I'm showing in this plot here is this is million metric tons of hydrogen, and the vertical axis is years. So right now we're 10 million metric tons. And if you were just to make a kind of a thought experiment and say, well, I want to replace 10% of the US natural gas usage with hydrogen on an energy equivalence basis, and still sustain the current level of hydrogen production that we have, you're going to need 33 million metric tons per year of hydrogen created. So that equates to about, well, more than, what's about 13 TCF total. The additional 23 would be 10 TCF of hydrogen per year. And I've just put on some per annum growth trends. So if you're assuming a growth of 5% per year on the 10 million metric tons it's produced right now, it's going to take you until 2045 or so to get there. If you're saying, no, we can accelerate this and assume 7% growth, then you can envision generating that 33 million metric tons by 2038. But again, let me emphasize, this is just for 10% of the US natural gas consumption. So it's a massive challenge. And one of the key messages I want to give, and I give all the time, is scale. The scale is, as far as the greenhouse gas challenge, is the biggest one in my mind that we have to face. So let me just summarize and call it quits. We've talked a little bit about the current hydrogen production. Most of it's coming from fossil fuels right now, with the larger part from natural gas. The renewable and nuclear generated hydrogen is the main growth opportunity. And the focus here is trying to get that unit production cost down. As I mentioned, DOE wants to get these costs down to $1 per kilogram of hydrogen within the next decade. And we went through a little survey of some of the alternative hydrogen sources. Some have gone out of favor. Some like native hydrogen are piquing people's interests right now. Frankly, I think all of these deserve continued research, because at this point that we're probably going to need all of the above to be able to address development of hydrogen for a low carbon economy. And with that, I'll stop.
All right, thank you, Mark. So if we have the chat here, we already have a question. See, I'm curious about the ratio of water to hydrogen. What does the electrolysis process need? Why does it need so much water? Does it need to be
Yeah.
fresh water in current models or economically viable processes?
Right. So the water question, and I didn't quite understand the second part of that, but so you need for, let's say, every kilo of hydrogen that you're going to generate, about 9 kilos, probably a little bit more of water. And you're using the water as essentially the feedstock. You're just dissociating the hydrogen and the oxygen. So you're going through the water with the electrolysis process. Now, you also need a lot of water, probably close to about the same amount, maybe a little bit less if you're using steam methane reforming. And there was a second part to that question, Evan. I'm not sure if I caught that.
Yes, Mark, it's me, Gillian.
Hi, Jill.
Hi. So I just wondered if you have to use fresh water in the current models, or could you use seawater?
Yeah, as I understand, that you need fresh water. Now, maybe, for, at least for the electrolyzers that they're talking about. I'm not an expert on that, and there may be some technologies that are being developed for seawater, but my understanding is most of the electrolyzers that are being considered are fresh water.
Thank you, Mark. So I guess it just seems to me we've got another issue there of water consumption.
Yeah, and there you go. You need let's go back to a small scale reactor. You need a reactor to desalinate the water so that you can put it into your electrolyzer. So, it becomes a little bit of a cascade problem, doesn't it?
Okay, so we have another question from Mosen. It says, hydrogen H2 is pretty reactive. Could you please talk about safety concerns with production and storage?
Yeah, well, it's one, currently there are regulations for hydrogen because it is being utilized, within the industry, particularly the petrochemical industry. And, so there are regulations in place for how it is stored and also, pipeline practices. Transportation as well. Yeah, it's got a large flammability range. It's very flammable. It's also difficult. You can't use the same sort of, for example, like mercaptans that you use in natural gas to be able to determine where the natural gas leakages are. So you have to have other monitoring methods to determine where leaks are. So it comes with its own challenges. There are practices and regulations in place already. Now, when we scale up, they probably need to have another look at those practices and regulations.
Okay, and Tristan, if you want to unmute yourself, he has a question regarding infrastructure.
Hi, Mark. Great talk.
Hey, Tristan.
I really love hearing about these hydrogen solutions. So can you talk further about the infrastructure needs? So, I know can we retrofit the current pipelines to distribute hydrogen, or do they need to be entirely replaced? And do you know if the feds are on top of this idea in any sense?
Yeah, and great questions. Depending on how the hydrogen is going to be utilized, you can introduce or admix low percentages of hydrogen into natural gas systems without much issue. There's a process called embrittlement with steel with hydrogen, and that becomes an issue of about 20% hydrogen in a pipeline system. So, notionally, we talk about like 10% because that seems to be safe. There have been extended experiments, including distribution of hydrogen to consumers in Europe with an admixture of about 10% hydrogen in the system. And it looks like that's worked pretty well.
Is that percentage, is that basically saying, these pipelines need to be replaced, so many years, and by adding this amount of hydrogen, we wouldn't affect that replace rate?
Yeah, that's pretty much it. Or the other way to look at it is that you wouldn't create additional risk in your pipeline system if you kept it below 20%.
Sure.
And yeah, so now if you need pure hydrogen, and so for example, like fuel cells, you need 99.99% hydrogen. So there, you really can't utilize the existing natural gas infrastructure. But where we're advantaged is that we have a lot of the pipelines, we have lots of rights of way. So potentially you build hydrogen pipelines, parallel hydrogen pipelines going along those rights of way where natural gas pipelines are.
Okay. And are the feds, are they talking about this?
Yeah, they definitely are.
Okay.
So I've participated in a few sessions with the DOE, and this has come up in discussion. That's I think again, at low percentage, people recognize this. They've talked also about moving along a natural gas pipeline and then separating it out and then purifying. That gets to be really costly.
Yeah.
So I think again, it depends on usage. If you're going to use it for industrial uses or combustion, in particular turbines, low percentages are fine.
Well, I look forward to the day where we get past just talking about it and start.
Yeah, well, that's going to be the real challenge. That's why I'm kind of advocating all of the above, because if everybody's putting their hopes on, okay, well, it's got to be electrolysis, it has to be renewable generated. You're starting from such a low point that you can't really develop the markets, you can't really develop the practices and understand the value chain. You got to get into the business, I think.
Okay, we have a question here from Sahar. Question regarding the underground coal gasification. Is there any concern for co-producing CO2 and H2 as the synthetic gas may trigger microbial reactions in the subsurface, leading to the consumption of H2 and generation of methane?
Well, there is a potential for methanogenesis in any of these hydrogen schemes, at certain temperature ranges. I don't know for UCG if that's going to be an issue so much, because you basically you're generating the hydrogen, the synthetic gas stream at such high temperatures that if there are any archaea or any microbes down there, that basically burn them up. Maybe when the syngas is stored later, then you might have an issue with that.
Okay. If anybody has any other questions, feel free to ask them now. You can unmute yourself. Let's see. Oh, Francis Peel asks, there's a report that getting a lot of press in the UK today that says that the full cycle of creation and use of blue hydrogen with current technology releases more CO2 than simply burning the methane in the first place. Even if CO sequestration is applied, is that true in your opinion?
Yeah, there's an article that came out, when was it? Maybe earlier this week, Frank. I know the one you're talking about. And their premise was that because you need the natural gas to drive the process for steam methane or autothermal reforming, and you're consuming it, then you need a lot of natural gas in the system. And based on the assumption of fugitive emissions, so if you read that paper, look closely at the fugitive emissions assumptions. I think they're assuming about 3.5%. Then they come up with the view that this is going to be generating more greenhouse gas than other processes. It really depends, I think, on the fugitive assumptions. And also, if you read carefully down in the conclusions, and I've read that article, you'll see that their premise is that they're starting from the point that they don't want to use fossil fuels at all. So I think, I hate to say it, but if you kind of have that in your back of your mind when you're starting with this, I think you end up getting an answer that you like at the end. One last comment on that. I think also, further to what I was chatting with Tristan about, you know, we need to start to develop these markets and industries with hydrogen. And I do not think we can afford to wait as a society of purely green generated hydrogen.
Okay. Well, I think that's all the questions we have. Tristan said he agrees. We need to make moves now. So yeah, Francis responds to thanks. It's the impression I got from the court. Seemed to be based on anti-fossil fuel premise. So there you go. Well, all right, Mark, thank you for that talk today. We appreciate it. And next week we have Scott giving a talk, and that will be the last of the series. So I hope everybody comes and makes that talk next week as well.
Yes. Well, thanks again, and everybody have a great weekend too.
Thanks, Mark.
Bye-bye.